Let me start then, and it's a pleasure for me to see you all here, and it's very nice to be here as well. And in my presentation, I would like to talk about how I'm using Python and its features to make sure that we allow for the efficient PCR design and solve one of hardest problems which we encounter during that solution, during that problem solution. So here is an agenda. First, I would like to get some introduction, some overview of what we are going to do here. Then I will talk about the general approach to the problem we are going to solve and provide some hints of how we did final solution, right? Then I will talk about the results and provide summary, and then I will try to answer your questions. So let me start from far away, a bit far away, right? Thing is that polymerase chain reaction is useful in many aspects. We can see here some examples of when it's used. For example, if we want to see what mutation in siblings DNA, or for example, you would like to produce some vectors using predefined template, or we want to see what are presenting bacteria in different media, or for example, you would like to assess the sequence of different mutations, or if you would like to pick up compounds which are tropic to some specific targets in drug design, that's DNA encoding libraries. We could use a PCR as the means to achieve our tasks. So how it's used actually? We have a template, it's a DNA sequence, and that template needs to be amplified for our purposes, right? And the driving force of that amplification is a set of primers and probes. We basically need two primers and a probe, for example, if we want to execute real-time polymerase chain reaction. And that oligonucleotides need to be designed in advance. Primers are anchors for their polymerase, and probes allow to identify the quantities of amplifying of the template being amplified. So what is the flow? We need to first denaturize our sequence, our DNA sequence. Then primers and probes get quenched. They attach to the denaturized DNA sequence. Then polymerase attaches to the primers, to the sites where primers are allocated, and the process of extension begins. As soon as it completes, we cool down the solution and repeat the steps again. So we have amplifying sequences, and each step produces twice as much DNA sequence as before. So that's the idea, and the question is how to properly identify primers and probes, how to properly design them to get the best results possible for our purpose. So that PCR design has some peculiarities. The thing is that template might constitute up to 5,000 base pairs, and that produces a lot of different combinations which we need to evaluate to pick up the best design. So that number of combinations might become up to 1 million, and it's a huge number, and the thing is that we need to produce the design quite fast and efficiently. So there are several key parameters to consider in that design, and the thing is that one of them is that we need to minimize the presence of self-foldings and dimers formed by primers and probes. And that's a difficult task to identify such structures, and it's quite time-consuming, and that hampers the design speed. So we need to find the best way to identify such structures. And the thing is that this problem of identifying such structures is a constrained and highly non-convex optimization problem, actually. So in order to find the best ones, we need to come up with some algorithm which allows to identify basically the global minimum in this problem, right? So when basically on the right side, we can see here, is it working? An example of a secondary structure. This is a self-folding of a DNA sequence, right? So what is the essence of the problem? We need to detect those structures at a high speed because the number of combinations we need to consider is quite huge. And we need to analyze every single oligonucleotide in the design against secondary structures and dimers. And also we need to identify cross dimers and self dimers, right? Thing is that those problems of identification of self-foldings and dimers is quite similar, but still it's necessary to come up with some efficient algorithm which allows to identify those things. So basically there is a classical Zucker algorithm which allows to identify secondary structures, but the thing is that it doesn't allow to identify dimers at the moment. So that algorithm is, has the complexity of n in the third degree in time. And that algorithm turns out to be tending to multi-branched and less stable structures. So it means that if it falls into that local minimum, its predictions are not accurate enough, and the final PCR design might fail, actually. So yeah, the thing is that we needed to solve those problems, and here is basically an outcome of some outcome. So this is the structure predicted by Zucker algorithm. This is a structure observed in the natural setting. This is a structure which we managed to predict ourselves. So I would say it's much closer, both in terms of energy and melting temperature. So the approach is pretty simple. We decided that it's necessary to solve the Steiner tree problem. But before we do that, we need to select the nodes of the tree we are going to build, or trees we are going to build. So we start from building an energetic table. Then we pick up chains. It's a set of sequences, I would say double-stranded sequences, right? And then we need to pick up such combinations of chains which produce basically the Steiner tree. And here we can see the numbers associated with each of the steps which result in the Steiner tree. So we can see that all the steps have the complexity of n squared. And it's, I would say, more efficient than initial algorithm provided by Zucker. So basically, in order to build that tree, we needed to pick up several metrics which allow to find out the best nodes of the tree, right? So we start from the high energetic chains. So we needed to come up with metrics associated with energy of the chains. Then we needed to evaluate energy densities of combinations of the trees, of the chains, and cut off the chain combinations which have high energy density. And when that is done, we need to filter out the trees with high energy, because those trees are associated with secondary structures, so dimers with high energy and low melting temperatures. So how we build the energetic table? We need to pick up the sequence and its reverse, and then combine each consequent letters into pairs. This is the so-called nearest neighbor approach, and we can see there are numbers. Yeah, and those numbers are associated with energies of the stacks. So, for example, if we look at this one, it's forming it's forming combination which is partially, how to say, which partially complementary, which is partially complementary, and the next one is completely complementary, and this produces some energy which is below zero, right? The next combination is complementary as well, and it produces energy below zero, and so on. So we pick up sequences of those combinations, and those combinations are called chains, actually. So this is how we build the energetic table, and thing is that for secondary structures, we need to not to cross this yellow line, because it basically it's a constraint associated with the mass conservation law. So when, yeah?
Excuse me, what does the zero mean in the energetic table? What
It means that it doesn't form some complementary sequence. For example, if we have a look at some, I do not know, zero, T.
But I see there, like, the first line when you go G, and with T, C, and both A, I think it's zero, so there's no complementary to
Yeah,
go from?
yeah, that means exactly that. The thing is that we need to consider two consequent letters, and two consequent letters are associated with some energy, which is coming from the predefined tables of the nearest neighbor method. So in accordance to that, to those tables and the method, we just summate the energies of the consequent letters. For example, if we have a look at this one, and I do not know, we take this one, and this one, this one, and this one, and come up with energy of this particular helix, right? TA, GA. Is it TA? TA, GA, yeah. And as far as I can see, it's, no, it's CT, yeah, it's CT and GG. So it produces some energy which is below zero, right? But the next letter, which is coming into the sequence, produces non-complementary structure, and the energy is zero, therefore. So it's as soon as this energetic table is built based on the nearest neighbor tables, we analyze that energetic table and see what are the chains presented in that table. So we can see, for example, here, this one or this one. Those are the chains, right? The sequences of letters which are complementary or partially complementary. So when we build those chains, we also need to see the free space associated with those chains for the secondary structures. So, for example, this one would be the cutoff, because otherwise we wouldn't be able to build the hairpins associated with the chain. So, and also I should notice that we do not consider as a combination the chains which overlap. So those should be filtered out. So thing is that those chains have energy volume. It's the energy multiplied by the length of the chain. And here we can see the distribution of the chains in a sequence. I would say it's somehow resembling Pareto distribution, but for some reason it's non-convex in contrast to the Pareto distribution, but still. And it turned out that we need to pick up the chains with energy volumes which are less than 7th decile of this distribution. So, for example, yeah, somewhere here we just set cutoff, and the chains with those energies are only considered. So you can see the code snippet associated with how we evaluate the frequencies, the cumulative frequencies, the distribution function, which you can see here. So it's pretty simple, but still that NumPy package allowed to do that task pretty easy, right? And as soon as the distribution function is built, we just perform pickup of the cutoff, right? And this is the decile which I have mentioned. and it's used to cut off the chains with energy volumes which are below the cutoff. So the first task is completed, and after that we need to pick up, assess energy densities. Those are the sums of energy volumes of a set of chains. For example, if we take this chain and this chain, and then we summate energy volumes of those chains and divide by the area of this square, right, to assess the energy density. And that energy density has its own distribution. It looks like this. And it turned out that the best way to cut off the combinations of chains is to pick up somewhere here, right, out of this distribution. So the combinations which lay here are taken out, and we consider only them for our purposes. Also, you could have seen the code snippet which we used. Yet again, we calculate the cumulative frequency in here, and we take the half of, I would say, minimum of this value. It's here, right? And it's a cutoff for energy densities. So, in order to solve the Steiner tree problem, we have already pre-selected the chains and their combinations, and we just need to traverse through them. And that is done using energy density cutoff. I believe it's somewhere here, right? And we find the best neighbor here, and that best neighbor is taken as the chain which has the lowest energy density. So it's working like this. And as soon as we have combinations of those chains, the Steiner tree is basically built, and we have collection of chains which form the secondary structure or dimer, which we need to find out. So the thing is that those combinations also have their own metrics, and it's possible to cut off the trees which have high energy sums of energies, right? And the less energy is the better. And so where is the code snippet? And we have found a total energy cutoff. Here it is, I believe. And everything which comes above is filtered out. That's not the best Pythonic way. Of course, I have already updated this, but here is the outdated code snippet. So as soon as it's cut off, we have combinations of trees which are energetic enough to produce stable structures. So basically, the problem is solved, the task is resolved, and we have found out the combinations. And it's pretty much technical stuff to convert those combinations into structures. So here, for example, we can see how it's done. Here is the classical representation of the secondary structures using brackets and dots. And it's pretty simple to convert the combinations of chains from the tree into those structures, right? So I would like to bring up the performance. I did some benchmarking. It's pretty rough because it's not an easy to identify the best, I would say, sequences to be analyzed, but still you can see that the trend is somewhere of n squared in the time complexity. And I would like to also mention that this algorithm is pretty much easy adjustable to finding out the dimers itself as well, right? We just strip that constraint of yellow secondary diagonal, right, which we have seen before. And that's solving our problem out of the box. So, thing is that current algorithm turns out to be finding the most stable structures. In comparison to Zucker, it doesn't stick to multi-branching structures. It finds, I would say, simple foldings, which turn out to be more stable, and that's one of the key features of that algorithm. And here is a summary. So we have found out some metrics associated with how to efficiently build those Steiner trees and find the secondary structures and dimers. We apply instant filtering to find those structures because we need to reduce the time required to find those trees. And as soon as those trees are found, basically we have our issue solved, and we have quite performant and robust predictions algorithm. So that's pretty much it. I believe I'm ready to answer your questions.
What do you mean by the energy? You mean the weight between two nodes? Sorry.
No, energy is, if you look at this table, energy is energy of the chain, right? Here is the chain.
Which is the age, right?
Yeah.
When you talk about graphs.
Chains are edges, yeah.
Yeah, the age, so the age has a weight. So
yeah, weight is energy density.
Thank you.
So the less energy density, the better.
Less you mean in minus or?
Minus, yeah, because energies are negative, and the more negative energy is, the better. It means that we form stable structures.
One more question. Thank you for your great talk. I just wondering, did you consider the genetic algorithm approach? Because I've seen some minimization and optimization problems, which genetic algorithm solves, like, I guess, a bit more lower big O notations.
Okay, I see.
So, is there any approach you consider to add in your?
No, I didn't consider that approach yet, but thank you for the idea. Possibly that would be a better approach. I think is that classical algorithm is recursive, so we just split that sequence into some subsequences and go, trace back and find some structure which could be in place for that DNA, right? But still, if we have a look at the outcomes, here is the comparison. The thing is that the greater this part of the structure, the less energy. So it's less stable in comparison to those two. Thank you.